Earlier, you learned about the rectilinear motion of bodies. In simple terms, rectilinear motion is a motion that occurs in a straight line. The motion of a body in a straight line is treated as one-dimensional motion. The description of motion of a body involves its position, displacement, velocity, acceleration, and time. In the one-dimensional or straight line motion of a body, you are able to represent all these entities on a number line. A number line has an origin, and measurements to the right of the origin are taken as positive and to the left taken as negative. By adopting a proper sign convention for all the entities, you are able to solve the problems analytically. Before you proceed to the next topic that deals with two-dimensional motion of a body, that is, motion in a plane, you need to evolve a new way to represent these entities, as the number line method will not adequately describe and represent them. To fulfill this need, a new way called vector representation is used. Before learning this, you need to learn the basics of scalars and vectors. Let us start with scalars. Entities described completely with the help of a number along with its unit are called scalars. The mass of an object is 10 kg. This description is complete and you do not need to add to it to identify it. Similarly, the distance between point A and point B is 20 centimeter is a complete description. Likewise, the temperature of a body and the time at which an event takes place are described completely by a number along with corresponding units. A number along with the unit that represents the measure of a physical quantity is called its magnitude. Thus, mass, distance, and temperature are scalars. As with numbers in elementary mathematics, scalars can be added, subtracted, multiplied, and divided. Operations on scalars are the same as in elementary mathematics and algebra, whereas operations on vectors obey the triangle law and parallelogram law of addition. You will learn various operations on vectors one by one in detail. First, let's start with multiplication of a vector with a real number. When you multiply a vector p with a positive number lambda, you get a vector whose magnitude is changed by the factor lambda. The direction remains the same as that of p. Mathematically, it is expressed as mod of lambda p is equal to lambda into mod p. For example, when p is multiplied by 4, the resultant vector is 4p, whose magnitude is 4 times that of mod p. On the other hand, when you multiply a vector p with a negative number lambda, you get vector minus lambda p, whose direction is opposite to the direction of p, and its magnitude is minus lambda times that of mod p. For example, when you multiply p with minus 3, you will get vector minus 3p, whose magnitude is 3 times mod p and direction opposite to the direction of p. The dimensions of lambda p is the product of the dimensions of lambda and p. Next, you will learn about addition of vectors by the graphical method. In the graphical method of vector addition, either the triangle law of addition or the parallelogram law of addition is used. Now let us add two vectors by the triangle law of addition. Consider two vectors P and Q lying in one plane. Draw a line AB parallel to P. The length of AB is equal to the length of P. Display an arrowhead at B. A is known as the tail of P and B is known as the head of P. Then draw a line BC parallel to Q and equal in length to Q. Display an arrowhead at C. B is the tail of Q and C is the head of Q. Note that the tail of the second vector always coincides with the head of the first vector. Now, join AC. Display an arrowhead at C on line AC. AC is vector R, obtained by adding P and Q. Similarly, draw a line DE parallel to Q. The length of the line DE is equal to the length of Q. Display an arrowhead at E. Then draw line EF parallel to P and equal to the length of P. Put an arrowhead at F. The tail of P coincides with the head of Q. Now, join DF. Display an arrowhead at F on the line DF. DF is vector R obtained by adding Q and P. Here, vector R obtained by adding P and Q is the same as obtained by adding Q and P. This vector addition is the commutative property of vectors. Vectors also obey the associative law of addition. To understand this, consider three vectors A, B and C lying in one plane. Add A and B to get D. Then add D and C to get R, which is the final result. Similarly, add B and C to get E. Then add A and E to get R, which is the final result. Here, A plus B plus C is equal to R in every case. This proves that vectors obey the associative law of addition. What happens when you add two vectors that are equal in magnitude but opposite in direction? It results in a vector possessing zero magnitude and is called a null vector or a zero vector. In case of a null vector, you cannot specify direction. Various operations with a null vector are A plus 0 is equal to A. Lambda 0 is equal to 0. And 0A is equal to 0. Let's discuss the physical meaning of a null vector. Consider a body is occupying position P with its position vector R at time t. From time t to t dash, It moves from position P to P dash. Its position vector at time T dash is R dash. From time T dash to T double dash, it moves back from position P dash to P. The displacement of the body during the time interval T to T double dash is 0, as the body has returned to its initial position. Its displacement is thus represented by a null vector, which is just a point with 0 magnitude and without any arrow. Now let us discuss the parallelogram method for the addition of vectors. Consider vectors A and B, which are to be added. Redraw the two vectors with their tails coinciding at a common origin O. Complete the parallelogram by drawing parallel lines. Then, draw a diagonal passing through O. At the end of this diagonal, display an arrowhead. The diagonal represents the resultant vector R. After addition, you will now learn about the subtraction of vectors. Direct subtraction of vectors is a little confusing. To avoid this confusion, you must use the concept of addition of vectors after reversing the direction of the second vector. Vector minus B is added to vector A to get R. This method makes the subtraction of vectors easy. Earlier, you learnt about the addition of vectors by the graphical method. The accuracy of the results obtained using the graphical method depends on the scale you chose and your ability to draw exact parallel lines. You can get accurate results using the analytical method of vector algebra. Before learning the analytical method of vector algebra, you should understand the concept of resolution of a given vector in any two required directions. To understand the resolution of vectors, consider three vectors A, B, and C lying in one plane. In this case, you need to resolve vector A along the directions of B and C. O and P are the tail and head of A respectively. From O, draw a line parallel to B, and from P, draw a line parallel to C. Let these two parallel lines intersect at Q. On the line OQ, display an arrowhead at Q. Similarly, on the line QP, display an arrowhead at P. In this case, the length of the line OQ is 2.5 times the length of P, and the length of the line QP is 3.2 times C. Hence, from the triangle OPQ, you can write A is equal to 2.5 times B plus 3.2 times C. 2.5B and 3.2C are known as the components or resolved parts of A along the directions of B and C. In this expression, B and C are the unit vectors, and 2.5 and 3.2 are real numbers. Usually, vectors are resolved along the axis of a rectangular coordinate system using unit vectors for convenience. Unit vectors have a magnitude equal to unity, and they indicate a particular direction. You do not specify any dimension or unit for these vectors. They only indicate direction. Unit vectors along the direction of the x, y, and z-axis of the rectangular coordinate system are denoted by I cap, j cap, and k cap respectively. These three unit vectors are perpendicular to each other, as the three rectangular coordinate axes are perpendicular to each other. Now, let's see how vectors are added by the analytical method. First, we will discuss vector addition for planar motion or two-dimensional motion. When dealing with planar motion or two-dimensional motion, you need to resolve the given vector along I and j only. Now, consider a vector A on the xy plane. From the head of the vector, draw perpendicular lines to the coordinate axis to obtain vectors A1 and A2. Hence, we can write A is equal to A1 plus A2. Let this be equation 1. As A1 is parallel to I, you can write A1 is equal to AXI. Let this be equation 2. Similarly, A2 is equal to AYJ. Let this be equation 3. Substituting 2 and 3 in 1, you get A is equal to AXI plus AYJ. AX and AY are the magnitudes of the components of A in the x and y direction. Here, A makes an angle theta with the x-axis. You can write AX is equal to A cos theta and AY is equal to A sin theta. Let these expressions be equations 4 and 5 respectively. AX and AY can be positive, negative or 0 depending on the angle theta. A can be specified by its magnitude and theta, or its two components AX and AY. When A and theta are given, AX and AY can be determined using equations 4 and 5. When AX and AY are given, you can find A and theta as shown here. Now, let us solve a simple problem to understand the procedure associated with this method. Two vectors A is equal to 7i plus 3j and B is equal to 5i plus 8j are given. You are asked to add these two vectors and find the resultant vector C. To understand the procedure clearly, you need to first solve the problem using graph paper. To draw vector A, first mark the point 7, 3 on the graph paper. 7 is a coefficient of I and 3 is the coefficient of j. Join this point with O with a straight line. Draw an arrowhead at the end of this line. This line with the arrowhead represents vector A. Similarly, represent vector B by joining the origin O to point 5, 8. Complete the parallelogram by drawing parallel lines from the arrowheads. Draw the diagonal passing through O. Display an arrowhead at the end of this diagonal. This diagonal represents the required resultant vector C. Check the coordinates of the arrowhead point of C, which should be 12, 11. You can also solve this problem without graph paper. You need to simply add the coefficients of I and j as shown here. However, representing the given vectors on graph paper helps you visualize the procedure. Now, let's discuss vectors in three-dimensional space. Create x, y, and z coordinate axis passing through point O. Then represent a vector A passing through O. Here, alpha is the angle between vector A and the x-axis. Beta is the angle between vector A and the y-axis. And gamma is the angle between vector A and the z-axis. In this case, its three components along x, y, and z direction can be written as AX is equal to A cos alpha, AY is equal to A cos beta, and AZ is equal to A cos gamma. Here, A is equal to AX plus AY plus AZ, which can be written as AXI plus AYJ plus AZK. Here, AX, AY, and AZ are scalars, and I, J, and K are unit vectors. The magnitude of A can be written as the square root of AX square plus AY square plus AZ square. Let us solve a simple problem using isometric graph paper. Two vectors, A is equal to 6i plus 4j plus 9k, and B is equal to 4i plus 3j plus 2k, are to be added to find vector R. To visualize the process, you can represent A on the graph paper by joining the point 6, 4, 9 to the origin O. Similarly, join 4, 3, 2 to the origin O to obtain B. You can draw the resultant vector R after determining the coefficients of I, J, and K by simply adding the corresponding coefficients of A and B. Thus, you have learned the analytical method of vector addition for two-dimensional motion and in three-dimensional space. Earlier, you learned the addition of vectors by the analytical method using the triangle law. Now, you will learn the addition of vectors using the parallelogram law. Consider two vectors, A and B, passing through a point O. The angle between them is theta. To find the resultant C of these two vectors, complete the parallelogram with A and B as adjacent sides. The diagonal drawn from O of the parallelogram represents the resultant C of the two given vectors, A and B. The resultant vector C makes an angle alpha with vector A. In this figure, OP represents vector B. OR represents vector A. and OQ represents the resultant vector C. Extend line OR. From Q, draw a perpendicular to the extended line OR to meet at S. From R, draw a perpendicular to OQ to meet at T. The resultant vector C makes an angle beta with vector B. Consider the triangle OSQ. From the triangle OSQ, we can write OQ square is equal to OS square plus SQ square. Let this be equation 1. As point R lies on the straight line OS, we can write OS is equal to OR plus RS and OS is equal to A plus RS. Let this be equation 2. Consider the next triangle QRS. From triangle QRS, we can write cos theta is equal to RS by RQ, which is equal to RS by B. By cross multiplying, we can write RS is equal to B cos theta. Let this be equation 3. From the same triangle QRS, we can write sin theta is equal to QS by RQ, which is equal to QS by B. By cross multiplying, we get QS is equal to B sin theta. Let this be equation 4. Substitute equation 3 into. We get OS is equal to A plus B cos theta. Let this be equation 5. Substitute equations 4 and 5 in 1. We get OQ square is equal to A plus B cos theta the whole square plus B sin theta the whole square is equal to A square plus B cos theta the whole square plus 2AB cos theta plus B sin theta the whole square is equal to A square plus B square sin square theta plus cos square theta plus 2AB cos theta. C square is equal to A square plus B square plus 2AB cos theta. C is equal to square root of A square plus B square plus 2AB cos theta. Let this be equation 6. This equation is known as the law of cosines. Using this, we can find the magnitude of the resultant vector. Now, consider the triangle OSQ. From triangle OSQ, we can write sin alpha is equal to QS by OQ. QS is equal to OQ sin alpha. QS is equal to C sin alpha. Let this be equation 7. Consider the next triangle RSQ. From triangle RSQ, we can write sin theta is equal to QS by QR, which is equal to QS by B. QS is equal to B sin theta. Let this be equation 8. Equating 7 and 8, we get C sin alpha is equal to B sin theta. C by sin theta is equal to B by sin alpha. Let this be equation 9. Now, consider the next triangle ORT. From triangle ORT, we can write sin alpha is equal to TR by OR is equal to TR by A. TR is equal to A sin alpha. Let this be equation 10. Consider the next triangle QRT. From triangle QRT, we can write sin beta is equal to TR by QR, which is equal to TR by B. TR is equal to B sin beta. Let this be equation 11. Equating 10 and 11, A sin alpha is equal to B sin beta. A by sin beta is equal to B by sin alpha. Let this be equation 12. From equations 9 and 12, we can write A by sin beta is equal to B by sin alpha is equal to C by sin theta. Let this be equation 13. Now, consider triangle OQR. Here, A by sin beta is equal to B by sin alpha is equal to C by sin 180 minus theta. A by sin beta is equal to B by sin alpha is equal to C by sin gamma. Let this be equation 14. This equation is known as the law of sines. From equation 14, we can write sin alpha is equal to B by C into sin gamma, which is equal to B by C into sin 180 minus theta. And finally, we can write sin alpha is equal to B by C into sin theta. Let this be equation 15. From this equation, we can find the direction of the resultant vector C. Consider the triangle OQS. From triangle OQS, we can write tan alpha is equal to QS by OS is equal to QS by OR plus RS. Tan alpha is equal to B sin theta by A plus B cos theta. Let this be equation 16. From this equation 2, we can find the direction of the resultant vector C. Thus, the parallelogram law helps you find the magnitude and direction of the resultant vector C. C is equal to square root of A square plus B square plus 2AB cos theta. This equation is known as the law of cosines. Using this, we can find the magnitude of the resultant vector. A by sin beta is equal to B by sin alpha is equal to C by sin gamma. This equation is known as the law of sines. Sin alpha is equal to B by C into sin theta. From this equation, we can find the direction of the resultant vector C. Tan alpha is equal to B sin theta by A plus B cos theta. From this equation 2, we can find the direction of the resultant vector C. The description of motion of a body involves its position at any instant in time, its displacement, average velocity, instantaneous velocity or velocity, average acceleration, and instantaneous acceleration or acceleration. Let us learn how to represent these using vectors. First, let's start with the representation of the position of a body using vectors. Consider a body to be moving in the xy plane, represented by the rectangular coordinate system. At an instant in time t, it is at point P, which has x, y as its coordinates. Join the origin O to point P with a straight line and draw an arrowhead at P. This line OP with its arrowhead represents the position vector r of the body at that instant in time t. From P, draw perpendicular lines to the x and y axis to indicate the x and y coordinates of point P. xi represents the horizontal component of the vector r, and yj represents the vertical component of the vector r. This position vector r is written as r is equal to xi plus yj. Next, let's discuss how to represent displacement of a body using vectors. Consider the same body to move along a curve in the xy plane. The body is at point P at time t and at point Q at time t dash. R and R dash are the position vectors at points P and Q respectively. Join P and Q with a straight line. Display an arrowhead at Q. This line PQ with its arrowhead represents the displacement vector delta r. From the vector triangle OPQ, we can write r plus delta r is equal to r dash. On rearranging, we get delta r is equal to r dash minus r. Let this be equation 1. This displacement vector delta r is directed from P to Q, which is represented by the arrowhead. We can write equation 1 in a component form as delta r is equal to x dash I plus y dash j minus xi plus yj, which is equal to x dash minus x the whole I plus y dash minus y the whole j. Now let us see how we can represent average velocity of a body using vectors. Consider the same body to move along a curve in the xy plane. In this case, the average velocity of the body is the ratio of displacement and the corresponding time interval. Here, displacement is delta r and the time interval is delta t. As shown in the figure, delta r is substituted by delta xi plus delta yj. On simplification, we get v bar xi plus v bar yj. The direction of the average velocity is the same as that of delta r. Next, let's discuss the representation of instantaneous velocity or velocity of a body using vectors. Consider the same body moving along a curve in the xy plane. Instantaneous velocity or velocity is limit delta t tending to 0, delta r by delta t, which is equal to dr by dt. Let us conceptualize this limiting process. When the body is moving along the curved path in the xy plane, it is at point P at time t, at point P1 at time t plus delta t1, at point P2 at time t plus delta t2, and at point P3 at time t plus delta t3. The position vectors of these various points are P is r, P1 is r1, P2 is r2, and P3 is r3. The displacement vectors with respect to point P are at point P1. Its displacement is delta r1. At point P2, its displacement is delta r2. And at point P3, its displacement is delta r3. The direction of average velocity vectors are shown in the graphs. Delta t1 is greater than delta t2 is greater than delta t3. As delta t tends to 0, delta r tends to 0 and becomes tangential to the path at point P. The direction of velocity at any point on the path is tangential to the path at that point and in the same direction as that of motion. We can write the velocity vector v in the component form as shown here. Using the resolved parts of magnitudes of v in the x and y direction, that is, vx and vy, we can write v is equal to the square root of vx square plus vy square, and tan theta is equal to vy by vx, and theta is equal to tan inverse Vy by Vx. Next, let's discuss the representation of average acceleration of a body using vectors. Consider a body is moving in the xy plane. During the time interval delta t, its velocity has changed by delta v. Its average acceleration a bar is equal to delta v by delta t. On substitution and simplification, we get a bar is equal to axi plus ayj. Finally, let's discuss the representation of instantaneous acceleration of a body using vectors. Consider the body moving in the xy plane. The instantaneous acceleration or acceleration is limiting values of the average acceleration as delta t approaches 0. On simplification and substitution, we get a is equal to axi plus ayj. We can understand this limiting process by using graphs showing the motion of the body. Consider the body moving is located at point P at time t. P1, P2 and P3 are its positions after time. Delta t1, delta t2 and delta t3 respectively. The velocity vectors at points P, P1, P2 and P3 are drawn. For clarity, we have drawn 4 separate graphs. The direction of average acceleration, a bar, is same as that of delta v for all the positions of the point P. In all the graphs, we have used the triangle law of vector addition. As delta t decreases, the direction of delta v and a bar changes. As you learned earlier, average acceleration, a bar is equal to delta v by delta t. In the limiting condition, as delta t approaches 0, a bar becomes a, which is equal to dv by dt. Consider a body moving in the xy plane with a constant acceleration a. It is located at point P at time t is equal to 0, which has a position coordinate r0 and velocity v0. It reaches point P' at time t is equal to t seconds, has a position coordinate r and velocity v. Constant acceleration a is equal to change in velocity by time. Thus, a can be written as v minus v0 divided by t minus 0, which is equal to v minus v0 divided by t. Cross-multiplying and rearranging, we get v is equal to v0 plus a into t. Let this be equation 1. We can also write equation 1 in terms of its components as Vx is equal to V0x plus axt and Vy is equal to V0y plus ayt. As you know, average velocity is displacement divided by time. By cross-multiplying, you can write displacement is equal to average velocity multiplied by time. Substituting the values in the expression, you get r minus r0 is equal to v plus v0 divided by 2 into t. Substituting equation 1 in this equation, you get r is equal to r0 plus v0t plus half at square, as shown here. Let this be equation 2. Equation 2 can be written using its components as x is equal to x0 plus v0x into t plus half axt square and y is equal to y0 plus v0y into t plus half ayt square. Let this be equation 3 and 4. These equations imply that a body can have two independent simultaneous motions in x and y directions with constant acceleration. Similar equations can be written for three-dimensional motion also. Now, let's discuss relative velocity in 2 dimensions. Consider two bodies, A and B, moving in the xy plane with velocities VA and VB respectively, with respect to the coordinate system. the velocity of A with respect to B is written as VAB is equal to VA minus VB. Since subtraction of vectors is slightly confusing, we can write this equation as VAB is equal to VA plus minus of VB. Here, we first reverse the given VB and obtain minus VB, and then add VA and minus VB to obtain VAB. Similarly, VBA is equal to VB plus minus of VA. Finally, on comparing the two results, we find that VAB is equal to minus VBA, which means that the two relative velocity vectors have the same magnitude and are opposite in direction. This implies that the magnitude of VAB is equal in magnitude to VBA. A body that is in flight after it is thrown or projected is called a projectile. The motion of the projectile is the result of two separate but simultaneously occurring components of motion. One is the horizontal component without any acceleration, and the other is the vertical component with constant acceleration due to gravity. We neglect the effect of air resistance on the motion of the projectile. The initial velocity of the projectile is v0. Initial angle of projection with the x-axis is theta 0. The horizontal component of the initial velocity v0 x is v0 cos theta 0. This horizontal component remains constant throughout the flight, as the acceleration in the x direction is 0 and air resistance is negligible. The vertical component of the initial velocity v0y is equal to v0 sin theta 0. This vertical component keeps on changing with its position and lapsed time of the projectile, as the vertical component of the projectile motion has an acceleration equal to the acceleration due to gravity. Here, A is equal to minus gj, Ax is equal to 0, and Ay is equal to minus g. Consider the origin is at the initial position of the projectile. Therefore, x0 and y0 is equal to 0. Now, let's find the position coordinates of the projectile at any time t. Consider the horizontal motion x is equal to v0x into t. On substitution, we get x is equal to v0 cos theta 0 into t. Let this be equation 1. Similarly, vertical motion can be written as y is equal to v0y into t plus half at square. On substitution, we get y is equal to v0 sin theta 0 into t minus half gt square. Let this be equation 2. Now, we can write the components of the velocity of the projectile at any time t. Vx is equal to v0x, which is equal to v0 cos theta 0, as the horizontal component Vx always remains constant. As the vertical component of the projectile has acceleration equal to minus g, it keeps on changing with time. Hence, Vy is equal to V0 sin theta 0 minus gt. Now, let's write the equation of the path for the projectile. By eliminating t from equations 1 and 2, we can get the equation for the path of the projectile. From equation 1, we can write t is equal to x divided by v0 cos theta 0. Let this be equation 3. Substituting equation 3 in 2 and simplifying, we get y is equal to tan theta 0 into x minus g divided by 2 into v0 cos theta 0 square into x square. Let this be equation 4. In this equation, tan theta 0 and g divided by 2 into v0 cos theta 0 square are constants, as g, theta 0 and v0 are constants. As you know, the equation of a parabola can be written as y is equal to ax plus bx square. Let this be equation 5. In this equation, a and b are constants. By comparing equations 4 and 5, we can conclude that the path followed by a projectile is a parabola. Let's now find the time taken for the projectile to attain maximum height. At the top point, momentarily, Vy is equal to 0. Substituting Vy is equal to 0 in the equation, we get the expression as shown here. Tm is the time taken to attain maximum height. Therefore, we can write Tm is equal to V0 sin theta 0 by g. Let this be equation 6. Now, let's find the time of flight of the projectile. Time of flight is the total time during which the projectile is in motion. When the flight ends, y is equal to 0. If Tf represents the time of flight, then Tf is equal to time of maximum height plus time of descent. By the symmetry of the path of the projectile, which is parabolic, and time of maximum height is equal to time of descent. Therefore, Tf is equal to 2Tm. On substitution, we get Tf is equal to 2V0 sin theta 0 by g. Let this be equation 7. Next, we will find the maximum height attained by the projectile. Consider the maximum height of the projectile as h meters. This height is reached in time Tm. Substituting in equation 2 and simplifying, we get h is equal to V0 sin theta 0 square divided by 2g. Let this be equation 8. What is the horizontal range of the projectile? Here, the initial position of the projectile is 0, 0. The final position of the projectile is x, 0. X is known as the horizontal range, r, of the projectile. This is the horizontal distance travelled by the projectile during its time of flight, Tf. On substitution and simplification, we get r is equal to V0 square into sin 2 theta divided by g. Let this be equation 9. What is the angle of projection for the maximum range of the projectile? R will be maximum when the sin 2 theta value is maximum. That is, 2 theta is equal to 90 degrees. Therefore, theta is 45 degrees for R to be maximum. Let this be equation 10. Substituting theta equal to 45 degrees in equation 9, we get R max is equal to V0 square by G. The equation of the path for the projectile. Y is equal to tan theta 0 into x minus g divided by 2 into V0 cos theta 0 square into x square. Time taken for the projectile to attain maximum height. Tm is equal to V0 sin theta 0 by g. The time of flight of the projectile. Tf is equal to 2 V0 sin theta 0 by g. The maximum height attained by the projectile. H is equal to V0 sin theta 0 square divided by 2g. The horizontal range of the projectile. R is equal to V0 square into sin 2 theta divided by g. The maximum range of the projectile. R max is equal to V0 square by g. When a body moves in a circular path at a constant speed, it is said to be in uniform circular motion. As the body is continuously changing its direction of motion, its velocity changes continuously. Since the velocity of the body is changing, it has acceleration, which is known as centripetal acceleration. Let us find the magnitude and direction of the centripetal acceleration. Here, r and r' are the position vectors, and v and v' are the velocities of the body at points P and P'. As the body is moving in the circular path, the velocity vectors will be tangential to the circle at the points P and P'. The change in velocity, delta V, is obtained by using the triangle law of vector addition. V and R, as well as V' and R' are perpendicular to each other, as V and V' are tangential to the circle, and R and R' are the radii of the circle. Therefore, delta V is perpendicular to delta R. If we place delta V along the line which bisects the angle between R and R', the arrow of delta V points towards the center of the circle O. The average acceleration acts along delta V. Therefore, average acceleration E bar is directed towards the center of the circle. We can verify all these by changing the position of the point P'. As delta t tends to 0, the angle delta theta also tends to 0, and hence the average acceleration becomes instant acceleration. Therefore, we can conclude that the acceleration of a body in uniform circular motion is always directed towards the center of the circle. Now let us find the magnitude of the acceleration. As you know, the angle between R and R' is delta theta. As V and V' are perpendicular to R and R', the angle between V and V' is also delta theta. Therefore, triangle OPP' formed by the position vectors and triangle ABC formed by the velocity vectors are similar. From these similar triangles, we can write magnitude of delta V by V is equal to magnitude of delta R by R, where R is the radius of the circle. This can be written as magnitude of delta V is equal to V into magnitude of delta R by R. Magnitude of A is equal to limit delta t approaches to 0. Magnitude of delta V by delta t, which is equal to limit delta t approaches to 0. V into magnitude of delta R by R delta t. This expression can be written as magnitude of A is equal to V by R into limit delta t approaches to 0, magnitude of delta R by delta t. Let this be equation 1. As delta t approaches 0, delta theta also approaches 0. Arc PP dash is approximately equal to PP dash, which is equal to magnitude of delta R. Magnitude of delta R is approximately equal to V delta t. This can be written as magnitude of delta R by delta t is approximately equal to V, which implies limit delta t approaches 0, magnitude of delta R by delta t is equal to V. Let this be equation 2. Substituting equation 2 in 1 and by simplifying, we get A is equal to V square by R. Let this be equation 3. The acceleration of a body moving with a constant speed V in a circle of radius R has a magnitude V square by R, and it always acts radially directed towards the center of the circle. This acceleration is called centripetal acceleration. The word centripetal refers to center seeking. Now, let us find the centripetal acceleration in terms of angular velocity, omega. As the body moves from P to P dash in time delta t, the line OP turns through an angle delta theta. As you know, omega is equal to delta theta by delta t. Let this be equation 4. V is equal to arc length PP dash by delta t, which is equal to delta S by delta t. Let this be equation 5. Delta S is the arc length, which is R delta theta. Let this be equation 6. Substituting 6 in 5, we get V is equal to R delta theta by delta t. Let this be equation 7. Substituting 4 in 7, we get V is equal to R omega. Let this be equation 8. Now, substituting equation 3 in 8, we get centripetal acceleration AC is equal to omega square into R. Now let us find the centripetal acceleration in terms of frequency. Time taken to make one revolution, that is, time period is t. Frequency, F, is the number of revolutions in 1 second. Therefore, F is equal to 1 by t. distance moved by the body in one revolution is equal to 2 pi r. V is equal to 2 pi r by t. On substitution, we get V is equal to 2 pi rf. Omega is equal to 2 pi f. Substituting the values in equation 3, we get AC is equal to 4 pi square f square into r.